Hey yo, what's crack-a-lacking? So today I have a pretty interesting video for you guys. It's a bit of a late night upload, so I'm not gonna be talking that loud. We're in quarantine, and I figured that, maybe we should use this time to get to know the HL syllabus a bit more. And this is actually a pretty daunting question I ran into on a past HL math exam. So I thought we'd maybe break this down and kind of analyze what's going on here. So, a typical IB question, I think is for HLs now too, is, derivating by first principles. And that's kind of what we're going to do today. And we're also going to mix that with inductive proofs. So let's start with A. So we know that derivation by first principles is just pretty much the limit as the step size approaches 0 of any given function. But that function also takes into account the step size. So we have kind of this. And this is the classic derivation by first principles kind of formula. So I'm going to call it f prime of x is equal to this. So not too bad so far. So let's kind of expand. So we have that limit h to 0 of this this function right here. So wherever we see an x, we're going to plug in an x plus h. So we have a 1 to x plus h plus 1 minus 1 2x plus 1 all over our step size h. Now, one thing we can do is we can cross multiply our numerator. So we have limit as h approaches 0 of 2x plus 1 minus 2x plus h plus 1 all over, we're going to multiply the denominators in the numerator. So we have 2x plus h plus 1 times 2x plus 1. So this looks like a bit of a, all over h, my bad. So this looks like a bit of a daunting expression, but let's actually simplify. If we look at the numerator over here, we have 2x minus 2x, right? So these cancel out. Then we have 1 minus 1, so the 1's cancel out. So we're only really left with 2h. So this whole thing actually just simplifies to 2h. If we look at the bottom, we can actually do a bit of an expansion. So we have that this whole thing, if you expand it, would be equal to 4x squared, right? 2x times 2x plus 2x plus 4xh plus 2h plus 2x plus 1 all over our step size h. But if you want to make it easier to visualize, you can actually just multiply by the reciprocal. And what we have is actually quite conveniently our h's cancel out. So we have h cancel out, and all we're really left with is the statement, the limit h of 0 of 2 over 4x squared plus 2x plus 4xh plus 2h plus 2x plus 1. Of course, you can group like terms, but the main premise here is that x is independent of h. So as h approaches 0, all our h terms are also going to approach 0, hence they cancel out. So what we actually have left here is a limit of h as it approaches 0 of 2 4x squared plus 4x plus 1, but this is a perfect trinomial, right? So then this simply becomes limit h of 0 as this function, 4x squared plus 4x plus 1. It can be written as a perfect square, so 2x plus 1 squared is our gradient function. And if we double check, that's exactly what we wanted to get here, except it's negative. And that's in part because I forgot to, right here it was negative. I forgot to carry that negative forward. So yeah, it should be negative. I forgot this part right here. So yeah, that's our first answer. The second part is where it gets daunting, so I'm actually going to dedicate an entire page for this question. Oh, and it looks like it is backwards, so I'm just going to really quickly maybe make this a bit more legible. That's not gonna work. Maybe if we, yeah, there we go. So we have proof by induction that the nth derivative of 2x plus 1 to the negative 1 is equal to, this whole hairy, daunting thing. So let's take this step by step. Let's actually first express this entire kind of statements in something we can understand. So let's say that the derivative of, let's first call it n, of dxn of this expression right here, 2x plus 1 to the negative 1 is equal to negative 1 n times 2n n factorial over 2x plus 1 to the n plus 1. All right, and with any proof by induction, you have 3 steps. Our first step is to prove that n is equal to 1. So if we calculate this, we have that d by dx, I'm not going to write the 1 because it's implied that n is equal to 1, of 2x plus 1, negative 1, is equal to, just plug in the 1, so negative 1 to the 1 is just negative. 2n is just 2n, 1 factorial is just 1. Over 2x plus 1, n plus 1 is just going to be 2x plus 1 squared. And if we refer to our answer in A, 2x plus 1 is equivalently just, and if we go back to what we said here, we said that this is exactly this. So therefore, this has to be true. In our second part, we're going to set n to k, where k belongs to the set of all positive integers. And that's going to be our second step. So we're going to call this dk by dxk of 2x plus 1, negative 1 is just equal to negative 1 to the k times 2k, k factorial over 2k plus 1, k plus 1. This is pretty simple. This is the easiest step, in my opinion. You just plug k for n. And then in this part, this is the really tricky part of the proof, is we're going to prove that n can also be equal to k plus 1. This is a three-step process. So let's make the assumption that n is equal to k plus 1. In that case, n equals k plus 1 is one derivative higher than n equals k, which means we're going to have to derivate this entire thing. So in other words, we're going to say that dk plus 1 over dxk plus 1 is equal to the derivative of dk dxk of 2x plus 1 to the negative 1. This means we're going to have to actually take the derivative of this. But to make our lives a bit simpler, instead of using the quotient rule, we can just make this the product rule. So I'm going to do a little rearrangement here. We're going to say that this is equal to negative 1k times 2k, k factorial. Instead of saying k plus 1, we're going to take the inverse, which means we're multiplying by the negative exponents. So 2x plus 1, negative k minus 1. And so instead, we're going to have to essentially derivate this. So we're going to find the d by dx of this. So let's do that. So we have that this is going to be equal to the derivative of all of this in red. And so that is going to be negative 1k, 2k, k factorial. Remember, when we're taking the derivative, we bring down the exponent. So let's do that. Negative k minus 1, 2x plus 1. And then we take 1 less from we always subtract 1 from the the exponent, so then this becomes negative k minus 2, and then we perform chain rule, so we multiply by what's inside, and the derivative of 2x plus 1 is just going to be 2. So this is actually quite nice because we can do a bit of we can actually do a bit of algebraic manipulation. So I have 2 negative 1 to the k times 2k k plus 1. We're going to factor out a negative 1, and then we have k plus 1 2x plus 1, and then we're going to write this as negative k minus 1 times 2 to the 1. And you can actually do this all in one step, but for the sake of showing you kind of what's happening here, I'm going to actually group things together. So we're going to do negative 1k times negative 1 to the 1, and I'm writing these exponents, although redundant, just to kind of show you where the numbers are going to come from. Times 2k times 2 to the 1, k times k factorial times k plus 1 times 2x plus 1 negative k minus 1 minus 1. So actually this becomes cool because we see that negative 1, same base, so we just add the exponents. So negative 1k plus 1, 2k to 1, 2k to 1. Same base, just add the exponents. K factorial plus k plus 1 just becomes k plus 1 factorial, right? Because k plus 1 is the subsequent term to k, right? It's just one more than k, which means if we included k plus 1 in our series of k, then we simply get k plus 1 factorial, right? K plus 1, k factorial. So we can just push the factorial one term before k, which is going to be k plus 1. And then we get, of course, 2x plus 1, negative k minus 1 minus 1. And, you know, all we have to do is rewrite it. Times 2k, k factorial. Instead of having this in the numerator, we're going to put this back in the denominator such that all our negatives become positives. And when you look at that, this proves that n is equal to k, which is equal to k plus 1. And so we finish our proof by saying, because n equals 1 holds true, and n equals k, where k belongs to the set of all positive integers, also holds true, and because n equals k plus 1 also holds true, this statement has been proven inductively. So I hope that kind of cleared things up. If you have any questions, please feel free to leave them in the comments down below, and more videos soon. All right, peace out.